Okay, so in this video, I'm going to talk about Newton's third law of motion. And this is the second part of discussing Newton's third law of motion. Let me share the note. This is the note that continued from the previous video. So Newton's third law of motion, whenever one object exerts a force on the second object, the second object exerts an equal and opposite force on the first. And the force always come in pair. So I'm going to give an example using the example that was in the textbook with the apple and an orange. So the main thing about this example is about defining your system. So let's see. Here there is an orange girl. Orange. And she's in a wagon cart. And she's being pulled by the apple. This apple is pulling her. So let's see. So this is what's happening. The apple is pulling her. Let's define the system. So I'm going to define that this is going to be the system of our interest, which is just the orange that's in the card. This is going to be the system. So here is the system with only orange. All right, this is the system with only orange. Then what's happening in here? She's being pulled by the apple, right here. So this is the force from apple to orange. But at the same time, there is a force applied on the apple, force applied on the apple from orange. So this is from orange to apple. And we know that these forces, these two forces is the pair and they're equal and in the opposite direction. However, since we're only looking at an orange, right, as a system, so here, let's say this F force of the apple to orange, that's equal and opposite to from the orange to the apple. But here, what it is that only force that we care about is the apple onto orange. It's the orange that we care about. We're only looking at an orange. We don't need to worry about what's happening outside or what orange is doing. We only need to worry about what's happening on the orange. That's the system that we're looking at. So this force is the only force that exerts on the orange system. Sorry. Right? So net force on the orange That's equals to the force from apple onto orange. You don't need to, again, worry about other things. It's only the force that's onto orange. Onto the orange. I could be pushing, I could be doing something, but all I need to worry about is what's happening on me to talk about my motion. Then that's the net force on orange. Then acceleration on the orange. Acceleration on orange is equals to the net force on the orange, right? Divided by mass of what? Orange. Then that's equals to the force from apple. That's going to be the force from apple onto orange divided by mass of the orange. That's how you can find the acceleration on the orange. Again, these two forces cancel out, but we're looking at object on one. So object one exerts a force onto the object two, but object two exerts a force on the object one. Then all you need to worry about is that particular object if you define that as a system. Let's see. How about this? It's the same action, same thing that's happening. So it's talking about the same interaction. So it's the same picture I want to draw. Orange again is in the cart, right? Then she's being pulled by the Mr. Apple. This Mr. Apple is pulling. Like this. But this time, you can define the system the way you like. It's just this interaction doesn't change. The action is action that's happening. So this time, I'm going to put both of them in one system. So define this orange and apple in the same system. Then it's true. We have the force from the apple onto orange, and then force from orange to apple. And this is equal in opposite direction. And now these two forces is a pair, and they're in the same system, inside the same system, so they cancel out. They cancel out. Well, but we know that orange is moving, apple is moving. How can an orange move? There is another pair that's happening, right? This apple is walking on the ground, so he exerts the force from apple to the ground. And the ground is pushing the apple ground to the apple. And this, from the ground to the apple, the friction force, which is the reaction force from the apple, this is going to be, this is the net force. So now we're going to say the acceleration on the apple and orange is equals to the net force on the apple and orange is equals to what? Mass of the apple, mass of the orange, maybe mass of the cart. They are the whole mass in that system. And that's equals to the force from ground to the apple, the friction force. M apple plus M orange plus M cart. So that's going to be the acceleration of this green thing. Oops, sorry. Right? So these two are, again, it's the pair. But the other force, the action force from the apple is outside of the system. So you don't need to worry about it. All you need to worry about it is the net force applied on the system. So you define the system and you need to say what is in your system and you need to find out things correctly. But there's so many interaction forces happening and they all cancel out. So you don't need to individually pick every single interaction, and you can't. For example, I often talk about the example of throwing a pen upward and then downward, and that's due to the gravitational force, we say. But I never discussed that this pen is made of a bunch of molecules, and these molecules are constantly colliding with each other. They're constantly giving the forces against each other. We don't never talk about all those micro forces that's inside the pen, because those forces constantly there, but they always come in pair. They're going to cancel out inside the pen. So net force only from those interaction forces is zero. Net force becomes the gravitational force. There are many interaction force happening inside. We don't need to worry. The only thing we need to worry is the net force on the pen, which is the gravitational force, right? Because they cancel each other. They cancel out each other. Same thing happens when you, let's see, notebook. Something is happening with this notebook. If you want to hit the baseball with the base bat, right? And then the baseball gives a force onto the bat, and then the bat gives the force onto the ball, and that's equal and opposite. But when you look at only the ball as a system, then there is a force applied onto the ball from the bat. That's all you need to worry about by defining a system. If you put ball and a bat as one system, then you don't have any interaction force. You don't have any net force, except from the hand and all that. But yeah. So define your system correctly, and then you don't need to worry about all the interaction force inside the ball, because the ball is constantly, they might be stretching inside and doing things, but all those forces inside the system cancel out. Only worry about the force exerted on the system from the other object outside of the system. Forces inside the system, they all cancel out. So only focus on the forces exerted on the system from the objects outside. So that's what he means by defining a system. Okay, so again, my note is not doing so good, so I'm going to end this lecture, and then I see you in the class.